Taylan Akdoğan solved the problems. Let me just remind you again. And so I will solve two similar problems. Problem 1, we have the ideal oscillator. On the z-axis, we have a platform. Let's say this is 0. And the z is some amplitude times sine omega 0 t. And, well, let's see. There is a mass on top of it. So this is oscillating like that. The question is this: what is the maximum amplitude such that the mass still has contact with the platform? Namely, it doesn't fly away from the platform. So let's do a free body analysis. This is m. There is the gravity down, mg. And there is the reaction of the platform on the mass n. This is n of t. So n of t minus mg, that's equal to mz double dot. So mz double dot is minus ma omega 0 square sine omega 0 t. Or n of t is equal to mg minus ma omega 0 square sine omega 0 t. So that mass doesn't fly off the platform means that n is positive. So at the minimum value of n will be 0. After that point, the block will have lost contact with the platform. Let us plot this thing. So mg is a constant force. Sine omega t goes this way, and minus sine omega t goes that way. You are multiplying it by minus ma omega 0 square. So it is here. And once we are adding, we are really shifting the position of 0 up to here. Okay? So let me just find a color chalk. Right. So this is n. We see that for n to be positive, this thing should not hit this thing or go below it. So this is the value when omega 0 t is pi over 2. So when omega 0 t is pi over 2, this is 1. Okay. So mg minus ma omega 0 square. So this part is ma omega 0 square. So if you increase if you increase the amplitude of the oscillation, so a is increasing. So this thing is going further down and further down. So if you start with a low amplitude and you increase it slowly, there will come a time when it will hit 0. So if you start from a low amplitude, if you are increasing the amplitude slowly, it will first depart when it is at the top of its travel here, A. So at this point it will. But if A was larger, then it may come here, then it will depart from the platform at this value of omega 0 t, and putting, where is it, z is equal to a sine omega 0 t, putting that value, we can find at which value the block flies away from the platform. Okay, that's the first problem I want to discuss. The second problem involving oscillations. To discuss the second problem, I must erase this one. The second problem I want to discuss is this. Suppose there is a rod connected to a torsion rod with okay, and this has a moment of inertia I, and it means that if you rotate this object a little bit, you give a twist and torsion bar will resist it. So torque is I theta dot. Theta is how much you have turned it, and the restoring force will be theta, and the solution of it will be theta dot plus omega 0 square. Theta is equal to 0, and here omega 0 square is kappa over I. So let us say that it is oscillating with this sine omega 0 t with this amplitude. Suppose it is set into motion and it is swinging by theta 0 to the right and theta 0 to the left. It is oscillating like this. And then suppose there is a mass m which we drop onto this disk and hits the axis d away from the torsion bar, and the question is what is the next amplitude? But to specify the problem, we say it hits the disk when the amplitude is 0 and the velocity is highest, okay? Because theta dot is theta 0 omega 0 cosine omega 0 t, and at time t equals 0, when it's passing through the equilibrium position, it has the highest velocity. Omega 0 t is 0, so its velocity is, angular speed is theta 0 omega 0. So the question is, well, it will oscillate with a new frequency that we know. Omega final square is kappa over I. The new moment of inertia is, now the body is here, md square. Md square. So that we know. What else we know? Something very important. This is a collision, and it happens very fast, and it's a completely inelastic collision. It sticks onto the disk, and angular momentum does not change before and after. So delta L is equal to angular momentum about the z-axis. Change in the angular momentum about the z-axis is 0. So initial angular momentum is equal to the final angular momentum. So initial angular momentum is initial moment of inertia, which is I. Initial velocity, well, the initial velocity is theta 0 omega 0. Theta 0 omega 0 is equal to final angular momentum, which is IF, and times theta 0 prime times omega f, which is just the LF. What do we know, what we don't know? I theta 0 omega 0 we know, IF we know, omega f, the final angular speed we know, So all we have to do is find theta 0 prime. So let's do it. Theta 0 prime is I over IF times omega 0 over omega f times theta 0 I over IF. Omega 0 is root k over I, kappa over I. Omega f is this, so it is root IF over I times theta 0, so it is equal to root I over I plus md square times theta 0, that's equal to theta 0 prime. So indeed the amplitude is now reduced. Okay, so I mentioned, I explained the ideal oscillator, and we learned how to use the complex solutions, which will be a great tool to discuss damped and forced oscillations. And we have solved a few problems to represent what's going on. Thank you.